Hello everyone, and let's keep going with our amazing topics where we finally learn how to use derivative to find interesting maximum points, minimum points, and so on. But in this video, we're going to talk about mean value theorem, which is basically a core of a huge mathematical topic which will lead us to optimization problems. And we finally learn all those magical ideas where we explain you why the boxes which you have delivered to your door have those kind of shapes, and why houses are built with the same shape, and so on. You'll see that. So first we're going to start with Rolle's theorem. The Rolle theorem says that if you are working with the continuous function on a closed interval, continuous function, remember, no gaps, no jumps, and so on. It's also differentiable function. What does it mean to be differentiable? First of all, it means it's continuous. Second, it means there should be no cusps, that's cusp, or sharp corners inside of the interval. You see, we don't include ends anymore. And also it has an interesting quality, which is shown here. F of A matches with F of B. On the graph, it looks like this. We started at this height, F of A, and we ended up to be at the same height, F of B. So we can imagine that this is a hike. For example, we're hiking, and I started from this beginning of the mountain. I was hiking up, and then I was hiking down, and end up to be the same height, right? Above the sea level. So the theorem says, you know what? Probably somewhere there was at least one time a point C inside of this interval where the slope of this function is 0. And it makes sense. If we left this point and we're going up or down, at some point we reach the maximum, or at some point we reach the minimum in order to come back. Make sense? And if we never actually went up or down, say we just went a straight line, then everywhere the derivative was 0. So it kind of makes sense, but it's a very important concept that this theorem proves that if I started from the same height and ended at the same height, but I did walk somewhere or drove somewhere or I was flying somewhere, there should be a point in time where my speed was 0 or the acceleration was 0 or whatever we're talking about. The slope of a tangent line is 0. So it's important though that the function is continuous, because what if it happens something like this, there's a jump. Yeah, that's not fair, and we can even go back to the same height. But, you know, there's no derivative here, which is 0. And also cusps do not work. I started from the same place, came back to the same place. There's no derivative here. It does not exist. So I cannot claim that it's a 0 as well. That's Rolle's theorem. I also wanted to make fun of the Rolle's name. I was checking how to say his name, because I remember he's a very famous mathematician. And also remember he's French, and I usually say it Rolle's theorem, but you have to hear how the Google says it.
Rolle.
No, really.
Rolle.
Rolle. So for you to know, if you know Spanish, I'm sorry, but it's super funny. So I think it's cool how it says it's Rolle. Okay, Rolle's theorem, not too bad. I think it's pretty straightforward. And then mean value theorem steps in and goes even farther. It says, you know, why do we have to start with the same point and end up to be the same point? That's not convenient. Can we have any kind of point and then make a statement about any kind of point? For example, I started with this height, was hiking, and end up to be over here. Can I say that if just like over here, I'm checking the height of the beginning point and the ending point, I will take this steepness between beginning point and the end point, can I claim that somewhere in time when I was hiking, I was going up like this, the slope of a tangent line had the same steepness, right? So it was the same slope as this guy over here. And that's exactly what mean value theorem says. It even we also want to point out that it's might be not only one point, there might be 2 points like this, and so on, maybe more and more. Imagine sine and cosine, they have infinitely many points like this. And this is what it says. So based on the graph, look at here. How do you call a line I started with? That's what you call a secant line, right? Secant means cutting. So I'm cutting through the beginning point and the end point. I'll call it A and B, and then I say, okay, what's the slope of the secant line? The slope of the secant line is this: f of b minus f of a over b minus a. We learned that in this class, at the beginning of this class. Well, what is the derivative? Slope of the tangent line is f prime at c. And the claim is that there's some kind of c, not always in the middle. It might be somewhere over here between a and b. Some kind of c which gives you the same tangent line as a secant line. That's the idea. So what they say here, secant line has a slope equals f of b minus f of a over b minus a, change in output over change in input, or rise over run, and it equals to f prime at c, which is basically derivative at the point. And your job is to find this point, because it doesn't really say, this theorem doesn't really say how to find it, but it says it exists, which is already a big deal. Here is the theorem, main value theorem, MVT. If function is continuous on the closed interval and differentiable inside of the interval, then there is at least one point, maybe there are more points than one, at least one point C inside of the interval, such that the derivative, the slope of the secant line will match with the slope of the tangent line somewhere. Very interesting concept, and comes from the two of these being parallel. The lines are parallel, so that means their slopes are equal. We know that. If two lines are parallel, then slopes are equal. Basically, the steepness of those two lines are the same. And then we can claim that then these guys are the same. But the left-hand side reminds us something about average rate of change. So which means we're kind of claiming that average rate of change at some point matches instantaneous rate of change. And that's a serious claim. So I have a very cool animation to show you. This is the idea on the left. Regardless of the height where we started, you see we started from one point and then ended up to be another point. You see how the slope is changing. The red color is the slope of the secant line, and the one that cuts from the beginning to end. The pink is the slope on the graph. At some point, the slope at the C will match with the secant line slope. And where the C is, that's our job to find out. The function can have many cases like that. So, as you can see in this situation, it has many places where this C happens. Here's my C1, here's one more C, and then one more C, where the slope of the tangent line matches with the slope of the secant line. That's a very nice animation. Thank you very much for the person who created this. I'll leave you guys a link over here. Here's the link if you want to know where did I go. Now, here's a very nice explanation for you to know that all of these concepts, they have a lot of applications. It's not very clear right now that this is the case, but actually it makes sense. Check this out. So a very nice situation explains here. I'm driving for 2 hours and I want to reach a town which is 100 miles away. So I'm driving and I know that I need to drive for 100 miles. Then I know that I will drive for 2 hours. Then the friend asks me, oh, so, don't speed, please. I don't want you to get a ticket. What's your average speed? Because the speed limit is 75 miles per hour in our neighborhood. Then you will say, okay, the average will be, I will take the distance I need to go, miles, right? Divide by the time I plan to drive, hours, and then 100 miles over 2 hours gives you 50, and now hear what I say, miles per hour. Miles per hour. This phrase, miles per hour, you hear it so many times. That indicates your average speed, right? 50 miles per hour. That's what the speed limit sign tells you. Don't drive faster than 50 miles per hour. So on average, you're driving 50 miles per hour. That's the idea. But your speedometer will tell you that that's not the case. You are driving sometimes super fast. So you're driving super fast, and you see the police patrol is watching. Then you slow down. Now there's a stop sign, then you stopped. Then you drive super fast after that, and so on. Your speed will be different all the time. The mean value theorem tells you if you drove for 2 hours, 100 miles with different speed, there was a moment in time. There was some point during your trip when your instantaneous speed was the same as average speed. So your average speed is 50 miles per hour, you know that. And at some point, you was driving 50 miles per hour, even though you were speeding, say at the beginning, 70 miles per hour. At the end, you was super slow because you was entering the city, so it was 45 miles per hour. At some point, you was driving with the same speed as the average. That's a nice explanation. Okay, let's go to the example, and so that you can proceed to do your homework. Find the average mean slope for the given function. And then this is one of the synonyms, so where we ask you to use mean value theorem. Average mean slope, that's the moment where your tangent slope equals secant slope. And here's the function x plus 1 over x. And the interval is given 1/2 to 2. Here's the graph. This is my function. As you can see, it's not continuous. Oops, you have to check. The theorem says the function should be continuous and differentiable on the given interval. Well, actually the interval is 1/2 to 2, so this dangerous point over here is 0, where there is a vertical asymptote, is being avoided. It seems like we only do from 1/2 to 2 over here. So I'm only looking at this piece. And in this piece, the function is both continuous, including intervals, ends, and differentiable inside of 1/2 and 2. That's what the mean value theorem requires. Then we ask you, can you please build a secant line? Here it is, I'm building it. And then find the moment in time called C. I'm guessing it's somewhere over here because it kind of looks like that. When the slope at C was the same as the slope of the secant line. Secant line gives you average, right? Average slope. So that's my average slope. Average slope. They ask you to find average slope, but instead we will use mean value theorem to say, well, we actually can find a derivative and then find a time where this derivative was the same as the average slope. Okay, let's do that. Solution. First, let's check that the mean value theorem can be applied. Then we can write down f of x is differentiable on 1/2 and 2, and it is continuous on inside of 1/2 and 2. Definitely, I think my notepad is glitching. Let me close it and open it again to make sure it's working well. Okay, good. Going back. So it's continuous inside of the interval and it's continuous on the interval including ends and differentiable inside of the interval. Then by mean value theorem, C exists. Still glitches. Okay, but we can finish, I'm pretty sure. Then let's do it. Step 1. What is the average slope? F of B minus f of A all over B minus A. B minus A equals f at 2 minus f at 1/2. That's the end of the interval. All over 2 minus 1/2 equals Can you plug all the numbers carefully? Well, the bottom becomes 3/2, right? We know that. At the top, you're working with fractions. So I will plug 2 in my function. It becomes 2 plus 1 all over 2 minus 1/2 plus 1, 1/2 plus 1 all over 1/2. Carefully simplify the fractions and you will get -1. Check. Did you get -1? Create common denominator, flip the fraction, all of this. Step 2. Step 2 is, let's find a derivative using quotient rule. Square the denominator. Derivative of the top is 1. Copy the bottom, x, minus. Copy the top. Derivative of the bottom, that's x. Let's check. That's 1. Derivative of x is 1. If you simplify the derivative, it becomes 1 over x squared. 1 over x squared. And that's my derivative. So we're gonna use mean value theorem over here. By mean value theorem, f prime at c is -1. So that's the whole point of mean value theorem. The derivative at c will match with the average slope. But average slope is found -1 over here. So we want to know where it happens. We want to know this c. So that's step 3. Plug your c into the derivative. -1 over c squared equals -1. And then I want to find this c. When you solve this equation, c squared is 1. And when you solve this equation, c gives you 2 points, plus and minus 1, right? Don't forget plus 1 and -1. So that means that if there are 2 points where it's gonna happen. At 1, so I almost guessed, you see? I almost guessed the answer. Actually, c should be 1. I will fix it over here. c is 1. Then this green line should be fixed too. Here it is. This is the place. But also at -1 seems like it happens again. But I cannot use -1. Do you know why? -1 is not in the solution. I will not even show it to you here. We only can use +1. Why? Because only one of these, only c equals to 1 is in a domain, is in the interval 1/2 and 2. So the answer is c equals 1. That's where this magic happens. Okay, you guys, do a couple problems like this in your homework, and I promise you all of this is going to follow into amazing topic where you can finally learn how to indicate where the function is increasing, decreasing, maximum, minimum, can't give up, can't give down. Inflection points in business, in engineering, in physics. It's all really, really fascinating. And I also need to fix my writing program. Thank you for watching. Hope you liked it.